In the previous sections, we were concerned with the same orbitals on neighboring atoms, like s plus s or p sub x plus p sub x. But there are other combinations that can mix together. Sometimes they result in bonding and antibonding combinations, and sometimes they don't. We should be able to recognize the difference. For example, if we take an s orbital on one atom and mix it with a p sub z orbital on the other, we should be able to tell simply by looking at the pictures that we are going to get a sigma bonding and sigma antibonding interaction. This type of interaction adds a layer of complexity to the molecular orbitals that form and to the energy level diagrams that we will be drawing later in the module, so we won't focus on them. But we should be able to recognize the types of interactions from the drawings. Although you are not responsible for d orbitals in this course, there are combinations with p and d orbitals that can lead to pi interactions. We should still be able to recognize these from the pictures. For example, when these two nuclei move closer together, the p sub x on the left atom would have a pi antibonding interaction with the dxz orbital on the right-hand atom. We know that because they would touch in two spots, above and below the internuclear axis, and the signs are opposite, which would lead to destructive interference. But there are situations where the overlap of two orbitals leads to neither bonding nor antibonding interactions. Imagine a p sub x orbital on one atom and an s orbital on the other. When these two overlap in space, the bottom half of the interaction, where the shading and thus the signs of the wave functions match, is a bonding interaction. But the top half of the interaction, where the signs are different, is an antibonding interaction. So which is it, bonding or antibonding? Well, actually, it's neither. There's no net bonding or antibonding, so this is what we call a non-bonding interaction. Instead of sigma or pi, bonding or antibonding, it's none of the above.